Thank you, everyone, and thank you for the hosts for bringing everyone together for this awesome event. This is me. My name's Shane Carr. I'm, as Rob and Ujjwal already mentioned, the convener of the TC39 TG2. That's the Internationalization Working Group. I'm also the chair of the ICU4X Technical Committee in Unicode. And I work at Internationalization Engineering at Google, but this talk is not on behalf of Google. So, without further ado, let's dive right in. So, before I came to Finland, this is my first time in this country. I took some Duolingo to learn some key phrases. This is one phrase I learned: "Suomi on kaunis maa." Finland is a beautiful country, and I've definitely experienced that. This was my plane arriving at about midnight. I got some of the midnight sun. I also got to visit Turku a little bit earlier in the week, and I met with the statue of this fellow named Mikael Agricola, who was turns out to be one of the founding fathers of the written language in Finland, which really relates to what I do, which is internationalization. Internationalization is I followed by 18 letters followed by N, because as programmers we love to abbreviate things and make them a little bit shorter and smaller. So what is internationalization? This is just an example of the screenshots of this page on YouTube. I have it in English on the left and in Japanese on the right, and you can see how some strings change from the left to the right. One thing that I think is interesting here is large units of numbers. When you do compact decimal notation, like you can see on the right, is in units of 10,000 instead of units of, 4 groups, units of 10,000 instead of units of 1,000 when you do, compact decimal notation. So there's a lot of really interesting challenges when it comes to internationalization. Here's a few more examples of internationalization. One thing I love to ask people when I get in conversations with them is name a language, and I'll tell you one thing that's interesting or challenging about it. For Finnish, the thing I'll point out is on the top right, collation. You have the word ä, which is normally would be less than Z, but in this case it's actually greater because of the way the language works, and it's sorted after it in the dictionary. So these are just all examples of different kinds of things we can do. Let me talk a little bit about how internationalization works. I call this the I to N stack. On the bottom, we've got Unicode, which is a standards organization, kind of like ECMA, but in this case, it's really focused on building these foundational algorithms for things like character sets, for things like scripts, writing systems, and so forth. Sitting on top of Unicode, we've got CLDR, the Common Locale Data Repository, which has data for hundreds of locales, specs, things like message format, person names, keyboards. On top of CLDR, we've got ICU, the international components for Unicode, which implements the algorithms with the data that's found in CLDR. On top of this, we've got the platform API, which is how we take the stuff that's in ICU and make it easy to use in your apps. ECMA 402 is an example of this. Android ICU is another example of this. And then finally, on the very top, we have your app, which can use this whole stack to do the internationalization and make great multilingual applications. So let's talk a little bit about what is ECMA 402. I already got a little bit of an intro to this, so I can go through these slides a little bit faster. But you already know about ECMA International. You know about ECMAScript. You know about JavaScript. You already learned a little bit about this. We're the ECMA 402 task group, the TC39 TG2, where we really focus on reviewing these internationalization proposals. The way we work is we have a monthly call where we look at internationalization specific proposals. We give feedback on those, and then we go to the main TC39 plenary to basically bring forward our recommendations. So we're sort of like the subcommittee that sort of does the work, and then we bring it up to TC39 to get final approval for these new features. So I'll just give you a few examples of the types of features that you can find in internationalization APIs. So this here is Intel datetime format. It gives an example for how you can use it. I'm sure that hopefully many people in this room have used Intel datetime format before, or to-locale string. Raise your hand if you've used these functions before. There you go. I love this. I love seeing this. That's almost 2/3 of the audience. So these are the functions that we work on standardizing and making work really well for you. Intel Segmenter is another example. This is a much newer API that we just added. This supports segmenting of grapheme clusters, which I'll explain a little bit later in the presentation, as well as words and sentences. And this is how you can use that here with an example of Hello World. Coming soon is Intel duration format. We already talked about how the stage process goes. So Intel duration format is a stage 3 proposal. This is what it might look like once it's landed. This will allow you to format durations. A much earlier stage proposal is this one, which is a stage 1 proposal. Smart unit preferences, this is what it might look like. This is an API that would allow you to pass in units in pass in quantities in one unit, but then be able to output them in the unit that's most appropriate for the context and the locale. So if you're measuring someone's person height, you can pass in 1.8 meters, but then if you're in the United States, that might get formatted as 5 feet 11 inches. That's some of the cool things that are coming with ECMA 402. Now I'm going to sort of pivot and talk about ICU4X. What is ICU4X? So ICU4X, I showed you on the earlier slide. I talked about here's the different layers. I talked about your app. I talked about Unicode. I talked about ECMA 402. Now I'm going to talk a little bit about ICU and ICU4X. So ICU4X is an internationalization library that's portable, meaning that it's focused on running on all types of devices and all types of programming languages. It's lightweight, meaning that you can't, the way we do that is by using compile time dead code elimination. It also means that it's able to run very efficiently on client-side applications. That's what we're here for. We love front end. We love things to work fast and efficiently on the front end. And then the third thing is that it's secure. We write in Rust, which is a modern memory-safe programming language that allows us to deploy to all these different platforms. So who are we developing ICU4X? It's a technical committee within the Unicode consortium. These are the three main companies that have been contributing to the effort. We'd always love to get more involvement as well, so feel free to have your name or your company added to this list. We'd love to grow this project. So ICU4X is tiny and fast. I'm just going to give you some pictures, some graphs to demonstrate, how the effort that we focused on really building this internationalization library that runs really efficiently on the web platform and on the client side. This is if you need to do basic number formatting. I wrote a little program, ICU4C and ICU4X, in terms of binary size. And I know this looks very skewed, but I really did try to make this as fair of a comparison as I could. It just turns out that ICU4C has a lot of logic as it basically ships a lot of its own code to handle data loading and locale normalization and things like that, which in Rust, a more modern programming language, are sort of handled by the compiler. This gives us a much smaller code size. The performance is also reflective. We are much faster for sort of these core fundamental operations. This here is more performance. This is for the segmenter, the word break segmenter. We get good performance with word break. Another thing that we have is, for example, we've been working a lot with the Skia and CanvasKit team. Raise your hand if you've heard or used Skia or CanvasKit before. A few people raised their hands. So this is basically a library that's written in WebAssembly that is basically a Canvas emulator. It needs to use ICU or ICU4X in order to do line wrapping, word breaking, line breaking, in order to lay out text on canvas. ICU for C, which is the older library, had been consuming almost 20% of their entire WASM file, and when adopting ICU4X, we were able to cut that almost in half. So that was quite a big accomplishment. It also works on servers. It turns out that a lot of the stuff we do to build really good front-end applications, making things really small, fast, and efficient, also reflects on big data centers. Because if you take a lot of these things that you build to be really, really good, really, really fast, really, really small, and deploy them at scale, you also get big wins in data centers. So this is an example of how that could work. So now I'm going to sort of get to the title of my talk, which is about ECMA 402 polyfills and ECMA 402 ponyfills. So what does this mean? A polyfill is a way that you sort of can patch functionality into the global object, into global this, in order to reflect the behavior that is maybe not yet available in the browsers that you're trying to target with your application. A ponyfill is very similar. It's just that instead of actually patching the global object, you just export it as a module that you use instead. there's a few ways that you can approach polyfills, and traditionally the first one has been very much more popular, is you just write JavaScript code to do it for you. Like, that makes total sense. It works. You write a native JavaScript. Problem is, this when you take this approach, someone has to maintain this code. Someone has to keep it in sync with the specification. And it's basically a separate piece of code that's separate from what's actually going to end up shipping in the browser. So the other approach, which is what I'm going to focus on here, is can we actually look at taking the code that gets shipped in the browser and actually put that on the front end as your polyfill. So ICU4X allows us to do that. One question is, it sounds great, but can we make it fast and efficient? I'm going to be talking about polyfill because about shipping a separate module and how we can ship a separate module here. So my main sort of thesis of this talk is that ICU4X is an ideal polyfill because it gives the exact same code that's going to be eventually shipping in Chrome and Firefox and Safari and Node.js and Dino, and bringing that code into your application so that you can use it ahead of time. So this was a picture I showed earlier, the I10N stack. This is where the ICU4X polyfill can fit in here. Basically, instead of calling through the platform API, if it's not yet available in your application, you can call ICU directly. So you get the same identical behavior either way. So I'll move right along, talk about an example of how we can use ICU4X in JavaScript via WebAssembly. So how does it actually work fundamentally, and how do we actually make this fast and efficient? So ICU4X has its own custom WASM bindings written in Rust. We focus really on how can we make this with optimal code size and performance. We went back to the fundamentals. We went back. We stripped out everything, all the machinery that we would normally use to build a WebAssembly application, so that we can focus on what do we actually need. What are the essentials? So we didn't use WASM bindgen, which is a popular library in Rust for doing this. We ended up building our own tool called Diplomat, which builds ergonomic JavaScript wrappers that are built on top of the CFFI. You can read more about it at that link. And if you see a little bit about how this flowchart works, we've got ICU4X, which is written in Rust. We wrap that with these symbols in CFFI. This is where we get a little bit more technical. The next few slides are going to be a little technical because I wanted to actually show you how these things work. But yeah, the CFFI symbols are basically extern exported functions. Those get exported into a WASM file. In order to actually use those from WASM, we have a very thin Diplomat JavaScript wrapper on top of those, and then you can use it in your app. I also will point out that Dart is another one of our targets. This is a front-end conference, not specifically a JavaScript conference. So if you use Flutter, which is another really great cross-platform web framework, you can use ICU4X to do your internationalization there as well. I gave a lightning talk about this yesterday at the Flutter meetup. You can Google for Intel4X to learn more about that. So, code. We love code. OK, so this is the QR code on the right just brings you to our GitHub repository where I have this code published in case you want to go ahead and look at it later. But this is a code that shows you how we managed to wrap the WebAssembly module into JavaScript code. So this is code that's generated. You never have to touch this code. I just sort of wanted to show it to you so you can see how it works. So WASM is the WebAssembly module. It has various functions. This is the function that we export that allocates memory inside of the WASM linear memory space, which again is not shared with JavaScript. If you don't know how WASM works, it basically is its own separate memory space that works on its own. And in order to read and write from it, you'd have to use basically array buffer APIs in order to get things back and forth. So when we want to call this function, the ICU4X grapheme cluster segmenter, in order to create a grapheme cluster segmenter, we have to go ahead and create some space over on the WASM side. We call our function. And then if it was successful, we go ahead and read the data out of the allocation. And then we go ahead and free the allocation and then return it. So this is the extent of the wrapper code so that you don't have to worry about doing this kind of low-level stuff. Here's what you might actually use on your end. So this is the actual code that is available for end users. In this case, I went ahead and exported this class called segmenter impl ICU4X from this little package that I made. I give it a little string. And then I set up my segmenter using ECMA 402 APIs. And I go ahead and collect all the segments, and these are the segments I get. There's 3 grapheme clusters. Raise your hand if you know what a grapheme cluster is. 3 people out of the audience know what a grapheme cluster is. It's basically a character that has diacritics associated with it. So for example, in a lot of European languages, you might have an accent or an umlaut or something like that. Those are 2 separate code points, but it's one grapheme cluster. So in a lot of these, like South Asian languages, like this one here, like there might actually be 4 or 5 diacritics that create a grapheme cluster, and that's why this is of interest in order to do this kind of calculation. Basically, the effect is that when you hit the arrow key on your keyboard, you will go 1 grapheme cluster to the right or to the left when you hit your arrow key. So that's the application for a grapheme cluster segmenter. So that's how that works. And of course, you know, the reason we spend time doing this is because we look at the numbers. Like, this all sounds great and cool, but like, does it actually work? These are the performance and the size for this. So when I tested this in Node version 22, and I used ECMAScript directly, I was able to segment a string that was 100,000 graphemes long in about 35 milliseconds. When I used this ICU4X code, I did it in 7 milliseconds, which actually surprised me. I wasn't expecting it to be less than the ECMAScript. I'm going to have to investigate that later. I didn't quite figure out why there's such a big differential there, but you know, I think that this does illustrate that, look, WebAssembly is actually fast. Something I hear a lot from people is that, like, well, when I call over the WebAssembly boundary, it's expensive because I have to do this copying in and out of the array buffer all the time, and like that has an impact on my app. I'm kind of afraid to do that because I think it's going to be slow. This is my counterexample. Like, this is a text-heavy API. We're sending over, like, we're sending 100,000 characters over the WASM boundary, and it still gives us really good performance. So I don't know what's wrong with Node 18, but I'm just glad they fixed whatever performance problem that was in Node 20. So I can also show you the code size. So you know, we heard earlier about when you build green applications on the front end, what you want to do is reduce the amount of bytes sent over the wire. That's one of the biggest things you can do to make your app you know, greener and more sustainable. Well, you know, that's why we focus on, can we do this efficiently with as few kilobytes as possible sent over the wire. So these are the sizes for the code and the WASM. Yeah, you know, we always focus on getting these numbers down. I think the point that they're at now, where we're talking, you know, in terms of, you know, single to double digits of kilobytes, is quite respectable when you look at some of these really big, heavy frameworks that a lot of people are using on the front end. So you know, we always look on getting these numbers down, but they're already quite respectable. So yeah, those are some numbers. And I'll just go ahead and, with a couple of minutes here, give you a little live demo, hopefully. So I have my code checked out in this little project here. And I can go ahead and run my code. Yeah, clear their console. I'll go ahead and run Node with my code. And I took this string, which fortunately, my terminal doesn't show it very well, but there actually are 3 characters there, and it shows you those same breakpoints that you saw on the previous screen. It also reproduces the performance characteristics that you just saw. Just to demonstrate how that works, I'll go ahead and also go ahead and here's the actual code. I'll go ahead and change the string. So instead of using this string, I'll go ahead and do this one. Hello, Finland, right? Okay, and then I'll go back to the terminal. I can go ahead and segment that string. In this case, it has more, I'll scroll up a little bit, but it has more breakpoints. In this case, these are just, these are 1 code unit apiece, so it just gives us 0, 1, 2, 3, 4, 5, 6, 7. But then when we get to the flag emoji, which again is not rendered very well because it's a terminal, it jumps from 7 to 11. So that's the flag emoji grapheme cluster right there at the end. Cool. Okay, let me go back to my slides. I'll get rid of that. I'll get rid of this. And there's my slides. My slides are back. So that's the live demo. So one other slide I'll just show on the screen. You don't have to pay attention to that code. It's not code that I'm proud of. But the point is that it works. But there's pain points when you use WASM. But the pain points are not performance. They're not code size. I already showed you those. But there are some pain points, just to be transparent here. One is that WebAssembly is very asynchronous, which means that if you use JavaScript, if you use ECMAScript modules, ESM, you end up getting a lot of top-level awaits in your code and things like this. There's some support for it in bundlers, but it's a little bit more limited. If you're using something like Webpack or whatever, like it works, but it's a little bit more limited. It's not super polished. TC39 is working on a proposal to add better ways to include WASM through ESM, but it's not yet implemented, which means that at least right now, hopefully in a year, the third bullet point will go away. But right now, there's not a standard way to include it. You have to have basically ship a blob of code like that on the right. Also, like tooling is optimized for monolith WASM, meaning like if you're shipping multiple polyfills, it's better to have them in a single WASM file than to have like 5 or 6 WASM files separately, just because of the way the memory model works. But hey, it works, and I showed you the code size. Like we can continue to make this better, and I'm working as much as I can in these standards bodies to make this work better. But it already works, and you can go do it today. You don't have to wait anymore. So. This is my last slide by conclusion. These QR codes are my various social if you'd like to follow me on Mastodon or anything like that. But WebAssembly lets us bring real implementation code to the web to support new features. And ICU4X is a great option for doing that on Intel proposals. So yeah, thank you all for hosting me. Again, thanks for the host for this beautiful venue. I don't think I've ever given a talk at a venue that's this beautiful before, so really appreciate that, and thank you all.